no surfaces are truly inert, because to make a surface, I had to break bonds. Yeah?
Would you also have an issue with the Pauli repulsion? Wouldn't that change depending on the surface you have?
Yeah, again, it's not saying that, I guess I shouldn't have said that this is independent of the surface, but that you can Fizesorb to anything. So yeah, I mean, Jason has in his notes less than 50. That's a little bit generous for the heat release. And we're going to talk a little bit about that in a second, because there's a different convention depending on whose literature you're reading. But yeah, so heats of adsorption either greater than -50, or if you take the absolute value, less than 50. Or you take the negative, I guess. I wouldn't say, oh, never mind. What if I've already put down a bunch of methane? Can I keep going if I'm Fizesorbing? Why not? Do I? I just told you Fizesorption's kind of independent of what's underneath, at least the ability to Fizesorb. The energies might shift, but what if I'm in methane and I see a pure metal surface, nobody's on there, I can just stick but not touch. And then I see a surface that's covered in methane. No problem, I just kind of hang out above them. So during Fizesorption, you can also form multilayers. The other thing that I'll mention real quickly is that these energies are for small molecules. So certainly methane is around, it's actually a little bit less than that. And smaller alkanes will be around those regions as well. But because van der Waals interactions scale with the size of the molecule, you can imagine if I had like polymers or something, van der Waals interactions can become quite substantial because they're very large molecules. But for small molecules, the type that we're typically dealing with in catalysis, these are good energy ranges. Yeah?
For large molecules, there'll be more attractive surfaces, more easily to make a dipole moment across large molecules.
Yeah, but I mean, you're going to get to a size where it's not because they're easier to induce a dipole, it's just because they can touch it at multiple places. It's because they can touch the induced dipoles over a larger surface area. You know, in fact, alkanes, if I look at Fizesorption of alkanes within a zeolite, it scales almost perfectly with the number of carbon atoms. You know, it doesn't matter the shape all that much unless, like I mentioned, some alkanes won't fit in all zeolites, right? But if I'm just looking at from methane up to decane, and I'm just considering linear alkanes, I can scale the binding energy with the number of carbon atoms. The bigger it is, the stronger it binds. All right, so that's all Fizesorption. But we put another one up here, so let's talk about that one. Because that one, chemisorption, is actually generally a little bit more important, depending on the reaction you're looking at. Okay, so let's pick a different molecule. Let's pick something that, even though it's still a molecule, I don't want to just rip a hydrogen off methane because that's kind of boring. Methyls are not stable in the gas phase. So what's a molecule that can bind to a surface? That's sort of the classic one. In fact, this is how carbon monoxide detectors work. Is CO sticks to the surface of the detector and it detects that its coverage has changed either by calorimetry or more typically by an electrical response, and the detector goes off. But they're adsorption detectors. So yeah, now we have formed a chemical bond to the metal surface. Are there any others that we can think of? Molecules still, intact species. Louder.
Ammonia?
Ammonia will do it. So what is special about ammonia in the gas phase that allows it to form another bond?
It's a lone pair of electrons.
It has a lone pair of electrons, and that lone pair of electrons, when you bring it in contact with a surface, will make something that looks just like that. In fact, ammonia binds to surfaces quite strongly. That's another very common binding intermediate that people can use to test things. What else has a lone pair that might interact with a surface? So water, it's weaker, but water can also bind to a surface. It typically, depending on the metal, it can actually change because it is a weak bond. I'm going to put a dash line there. But yeah, it certainly interacts stronger than methane would. And just like we have water here, we can really make this a little bit more general. We'll put an R for all alcohols, but I include water as an alcohol, despite what your Saturday does. Yeah.
So the molecules that have one pair of electrons bond stronger.
Absent van der Waals interactions, I don't know of a good example of a molecule that has no lone pair. That's not an ionic species in solution. Those can, yeah, in a similar way, those can bind. But no, I mean, like, for example, benzene can bind strongly to a metal surface. But there's two reasons for that. And one we're still going to talk about, but the other is because of the van der Waals interaction. So van der Waals interactions can be very important. But normally for small molecules, they're not. Yeah?
What about things like NO that are stable radicals?
Yeah, absolutely. NO binds to a surface, it looks like this. So that's a very important chemical in automotive exhaust catalyst. So you make NO in the engine, you make NO2 as well. You need a surface that can bind and then react that away to make nitrogen and water. I don't know. I stopped drawing the bonds once they stick because it's hard. It's actually not very easy to characterize the bonding between a metal surface and an adsorbate. Sometimes it's very obvious that it's a single bond, like in the case of ammonia, or if I had a methyl. So if I replace this with a carbon, it's pretty obvious that's a single, a single bond. But very often it gets confusing, like CO. CO is even kind of confusing in the gas, but you stick it to a metal and it depends on what surface it's on. Is that a double bond? Is the triple bond still there? It's not obvious. So I often, and this is common within catalysis, you just kind of draw it.
So is chemies absorption just forming bonds with the active site, basically?
Exactly. So that's a good point, is that this has to be an active material now. The whole reason we call it active is because it's reactive, right? That's why we call things active. It's because they react. So if I can't react with something, I'm not going to be able to chemisorb. Yeah?
Can you, so, if the chemical, if the surface is a piece of metal, do people ever try to make it charged?
Yes.
Does that help with the reaction?
It can. So, I mean, that's one of the principles behind electrochemistry. Is I charge a metal and I can take water and make hydrogen and oxygen from it. But that charge, it's technically a potential, but the charge that you generate on those interfaces does matter. The opposite of electrochemistry is what? So electrochemistry is taking electrical energy, taking electrons, and doing a chemical reaction. What happens when a chemical reaction can drive electrons? What type of machine is that? A fuel cell. So if that's the case of if I have a fuel, right, that's doing a chemical reaction, a battery is also in a sense a fuel cell. It's just one that is degrading the material of the battery itself, which is why you either have to recharge or throw it away. Whereas a fuel cell is meant to just keep going and going and going because it has a catalyst inside. Yeah.
Can you use an active site that instead of doing temperature absorption, does it same with magnetism because spin frustration or something like that?
You can't easily manipulate the spin properties of your catalyst, but there are catalysts that have spin properties, and their spin properties do affect how they do reactions. So if I'm dealing with iron or nickel or I'm blanking, the other ferromagnetic metal, cobalt. then I have to actually, if I'm doing it with a computer, I have to model it as a spin polarized structure because the spin does influence how it behaves. But it's a hard thing to kind of have as a tool. Plus, you need, an isolated site could still have a spin to it, but it's not going to align its spin with other sites if they're all isolated, right? I mean, a magnet is a magnet because all the spins align. What about this as a one final molecule that can chemisorb despite being a stable molecule? It's not because of resonance. So what is that, first of all? Ethylene. So yeah, it can interact with a surface through one of two ways. So I'm going to draw now a metal. Forget the surface, because all of these are individual atoms, and I want you to see the atom in this case. And I can interact through the pi bond. And this is how it looks. So all those pi electrons can form a bond with the metal surface. I can also interact like this. And I'll tell you a little bit about the geometry because I cannot draw these things well on a chalkboard. But in the pi bond, both the carbons have maintained their sp2 hybridization. In the other arrangement that I drew, they're sp3. So what happened in that sp3 arrangement? Yeah, I mean, the structure obviously changes because it's sp3, but what happens to the electrons?
Farther away. There's a homolytic cleavage.
That's a way of putting it. I've broken the bond, though. I haven't broken it all the way. I think the other thing is how I drew this is crappy. Sorry. This distance in the pi arrangement is shorter than the distance